to this session on strength of materials. In the previous sessions, completed we completed our chapter. We completed simple stresses, complex stresses. The bending stress was seen under a broad chapter known as stresses in beams. Then we also completed torsion as well, and we also completed the concept of strain energy. Now, in today's session, we will be trying to achieve this chapter of SMD BMD. However, it is not that easy to just complete this chapter in 1 hour, but I am making sure that each and every important a bit of information that is required for solving a question paper in GATE will be provided in this 1 hour. So before starting this session, I will remind you about a small hint that I dropped in our previous chapter. What I told you in the chapter of stresses in beam, that suppose this is a beam and the beam is loaded with a point load W. So tell me what will happen. I just told you, if you have been attentive about in the previous session, I told you that there is possibility of getting this beam broken by two ways. The first way of breaking this was bending stress, and the other way in which this beam can fail or can break is because of shear stress. The shear stress is because of this load W, which is parallel to this cross section, and in this way the beam can fail. So what is the factor responsible for shear stress? Shear force. And for bending stress, I told you, if L is the length, then a moment of magnitude W into L, force into perpendicular distance, is our bending moment. So this bending moment will be responsible for breaking this uh, beam with the by means of bending stress. So now, as design engineers or civil engineers, our main aim is to make sure that the beam does not break. So that is our responsibility. That is why company is paying us to make sure that things do not break down. And if it breaks down, that we have to take care of as well. So how we are going to make sure how we are going to ensure that the beam stays safe and it does not fail. So we go for stress analysis, we go for load analysis, and for that load analysis and to know the magnitude of load and bending moment that has been imparted on this beam at each and every section of the beam can be known exactly with the help of SFD and BMD. Now SFD, it will help you in finding shear force. SFD stands for shear force diagram. It will tell us where at what section, at a particular section, what is the amount of shear force acting on that B. Now BMD, what this BMD is responsible will tell us, similarly like SFD is telling us about shear force, BMD will tell us about bending moment. So for clarity, let me again वर्निक और दूसरा shear stress की वजह से शियर स्ट्रेस को, अगर शियर स्ट्रेस के लिए अगर हमको बीम को सेव करना है तो हमें पता होना चाहिए कि कौन से सेक्शन पर कितना शियर स्ट्रेस आ रहा है, और वो पता करने के लिए हमारे पास होती है शियर फोर्स डायग्राम। और बेंडिंग मोमेंट, कौन से सेक्शन पर कितना बेंडिंग मोमेंट आ रहा है ये पता करने के लिए हमारे पास होती है बेंडिंग मोमेंट डायग्राम। So this is how we are going to make safer beams. So let us now move forward and start this topic. Okay. First of all, let me tell you about what are the types of loads that we are going to see. The very first load that we have is a point load. The point load is a very simple load. It is concentrated at one point, so we do not need to find explicitly the center of its application or the point of application, because it is a concentrated load. It is also known as concentrated load. The second type of load is uniformly distributed load. It is also known as UDL. Now pay closer attention, because I want an important thing for you guys to know. See, there are two ways of representing a UDL. For example, the first one is like this. This is small w Newton per meter. Now, this is one way to represent it, but the most I will tell you about in this way. This way is important because of one thing I will tell you. This, I hope you have seen it in your exams as well. So this is an important way. Suppose you have a beam with length L, and a load of amount W is distributed across its length. So how we can convert it into a point load? So equivalent point load has a magnitude equal to the area of this diagram. So this is a rectangle with height W and with height W and length L. So the magnitude of the point load will be W into L, and the point of its application will be the centroid of this diagram. So the centroid mm, of this diagram, it is a rectangle, it will be at the middle of this beam. And I told you the magnitude will be equal to the area of this diagram. The area of this diagram is W into L. W into L. Now half of the beam is here and half of the beam is here, because the load is acting exactly at the center of this beam. So that's why I told you that this way of representing is very much important for us, because we can find area on it. So that is why it is important. Now the third load is uniformly varying load, or triangularly distributed load, or I will just say triangular load. This is not a standard term, but I am still telling you about it. So because the diagram looks like a triangle. So at one end we have a load 0, and at the other end we have the maximum value of load. Here it was equally distributed. At each and every point the magnitude was W, small w. At this point it is uniformly varying, so gradually increasing. So this, yes, Newton per meter. So again, if I have to draw equivalent point load, then the diagram will look something like this. I told you the point of application is the centroid of this diagram. The centroid of this diagram is L by 3 from 90 degree. Okay. So here it will somewhere L by 3, and here it will be 2L by 3. Hmm. And the magnitude will be equal to the area of this diagram. So what is the area of this diagram? The area of this diagram is half into base into height. Now base is small w, and the height, the length is L. Half into W into L. So these are three types of important loads, the loads that we come across in our beams. Now, if you come across an eccentric load, this is load W, and this is the difference D. It is eccentric by a distance D. So see, how we can transmit this load to this point. So we can, by principle of transmissibility, we can transmit this load here. We use some different, the load W can be brought to this point, this is, let's say, our point O. So at this point it can be brought, but there is a catch that you need to remember, that there is a simple moment also here. The magnitude of the moment is this W, the magnitude of load multiplied by this perpendicular distance. So I have to include that moment as well, W into D. So these were the types of load that are essential when we are while talking about the nature of the loads. Now we have types of supports. Now types of supports are very important, because the support will tell you about the type of reactions that your beam will be facing from the supports. The very first support is hinged support. This is how it is represented. So this is a hinge, or let us make it simpler. So a hinge is something like this, that let's say I have just nailed this beam. This is a beam, and I have bolted or hinged this beam at one point. So what it can do, it cannot move further. Okay, so because when I apply this force to move it here, the beam is going to the support is going to apply an equal and opposite amount of force in the opposite direction. So there is a uh, there is this reaction provided by this support in x direction. So what I will say is, there is a reaction in x direction. I will say Rx. Now if I try to just push this beam upwards, it will not move in y direction, because what happens when I apply this force, when I apply this force in y direction, this support is uh, capable enough to provide a resistance or reaction, so in the equal and opposite of equal magnitude and in opposite direction, to avoid this motion in y direction. So it cannot move in x direction, it cannot move in y direction. So that means there was some reaction that was provided by this support. This is Rx, sorry, it is in y direction, so reaction in Ry. So now see once again. Now same beam that was hinged, it cannot go in x direction, it cannot go in y direction. But what about, can it rotate about this point? Let me tell you. If I apply a moment, see, this is force and this is perpendicular distance. So if I apply this moment, what happens? It is rotating. So this rotation means that there is no such resistance provided by this support. That means there is no need to worry about the reactionary moment that should be provided by this, because there is no such reactionary moment provided by this uh, hinge point. So there is no reactionary moment. Hence, for hinge support, we have two reactions only. Now, the second type of support is a fixed support. Now this is quite interesting one. Here comes our beam. Now what happens to this beam? This is fixed. Now it is pretty much rigid, just like this. Now see, can it move in x direction? It is not moving in x direction. That means there is a reaction in x direction. Once again, fixed beam. Can it go in y direction? No, there is no displacement in y direction. There should be a reaction in y direction. Now once again, can it rotate? I am applying moment, but it cannot rotate. So there is a reactionary moment as well. So mz, why I am writing mz? Because this is x axis, this is y axis, and this is z axis. What will happen? This z axis, the beam will rotate about z axis. See, this is z axis, this is x, this is y, and uh, the axis perpendicular to your screens is the z axis. Now it is rotating about that z axis. That is why I am writing mz. Now the third one is roller support. roller support. Yes. So this is our roller. Now imagine if this is a roller. hmm, I don't have a roller right now to tell you, but imagine a trolley. So this is a trolley. If you are pushing it from pushing in x direction, will it move? It will definitely move. It has to move in x direction. Okay. So there is no reaction in the x direction. But can it move in y direction? The If I apply a force in y direction, it won't be able to move in y direction. No, it can lift up, but it won't directly just say move in y direction, because there is a weight acting in the downward direction. So there is just one reaction. This is Ry. But can it rotate? Yes, it can rotate. So there is no reaction as well. So there is just one reaction, that is because of its weight only. Okay. So these are our three types of support. Let me see if any support is remaining. No. So the types of support are covered. Now let us see what are the types of beams that we are going to study. The number one is now let us see what are the types of beams. So we are back now. Let's see what are these types of beams. What are the types of beams that we are going to study? The number one is, which is very important from exam point of view, is our cantilever beam. So this is our cantilever beam, which is very important from this exam point of view. Now for this beam, we have one end fixed. This is a fixed support, and the other end is free. Okay, and this beam can be loaded in any way. And so you have seen this kind of beam in our buildings. The window panes that you see, so they are kind of cantilever beam. Then the second one we have is simply supported beam. Simply supported simply supported beam. So for simply supported beam, we have one end that is hinged. So one end is hinged, and the other support is our roller support. So these are two very important beams which are important from our exam point of view. What I want you guys, what I expect from you guys is when you see this kind of beam, I just want you to imagine them from their reaction or FBD, their free body diagrams. That is what I expect from you. So when you see a cantilever beam, what should be your basic instinct? Just like when a tiger sees its prey, it is gonna just kill it. So when you are going to see a cantilever beam, it should be your instinct to go for its FBD. So what will be its FBD? Because it's a fixed support. So I told you that there are three reactions. So number one is there going to be a reaction in X direction, there going to be a reaction in Y direction, and there going to be a moment about Z axis. Now, when you see a simply supported beam, so similarly, our instinct should pick up and we should be able to directly draw its FBD. Now, what is this? Along Y direction, we have a reaction because it's a hinge support. Again, for ruler support, we have one more reaction, and for hinge support, for this hinged support, we have one additional reaction which is acting in x direction, rx, ry, ry. But the very important thing we guys need to understand is we are going to talk about shear force diagram. So for shear force, only the transverse load. So this is a beam, and the transverse load, which is perpendicular to the beam, will play a part in the shearing action. So whereas in axial force there is no such requirement, and as it is not going to bother us. It is not actually at this moment we are not bothering about it in this chapter at least. So we are talking about transverse loads only. So this is not necessary. If you draw this two and save your time, well enough, go ahead. So this is an important trick. So what are other types of beam that you guys should know? Hello. Okay. Okay. Oh, so this is a beam here. Now one of its support has is a type of hinge support. Is a kind of a hinge support, and here we have a ruler support, and the remaining portion keeps hanging. So that is how it works. So this is known as overhanging beam. Overhanging beam. So this is an overhanging beam, and this is single overhang. This is double overhang because uh, after the uh, support ends, there is some part that is overhanging. Okay, that is suspended. Say not suspended. Overhanging is the perfect one. So this is single overhang. Write it in the side. Single overhang, and this is double overhang. Okay, now let me go for some sign conventions. Just keep this in mind. If a beam is bending like this, then it is known as sagging. And for sagging, the bending moment, the bending moment diagram is positive. And if a beam is bending like this, then it is called as hogging. And for hogging, shear force diagram is negative. So this much thing is what I want you to remember for now. Further, if there is any thing that comes into my mind, I will tell you once again. Now, some other points that I want you to know. Very important note. The degree of shear force diagram is less than 1 by the degree of bending moment diagram. Now, what is the degree of a curve? So we know that this is parabola and y is equals to x square is its equation. The degree of its equation is 2 because it is the highest power of this x. So that means 2 is the degree of this curve. For this curve, we have degree 2. So then we have some cubic parabola like this, say. So for cubic parabola, we have y is equal to x cube. So this has degree 1, 3. Sorry, the degree of this parabola is 3. For a line, for an inclined line, the equation is y is equals to mx plus c. So x has 1, has the highest power 1. So its degree will be what? X axis, y axis, and we have a horizontal line. So what is the equation of this? Let's say this is some point 6, okay, on on y-axis. So what will be its equation? Its equation will be y equal to 6. So there is no term of x. It can be written as y is equal to 6 x to the power 0. So the degree of, here I will write degree, here we will have diagram. It's a horizontal line. Horizontal line has degree 1, sorry 0, as I told you. For an inclined line, the equation is y is equals to mx plus c, and the degree of x is 1. So the degree of this curve is, this line is 1, inclined line. Now we have a parabola, y is equals to x square. So its degree will be 2. For cubic parabola, the degree is 3. So this is how degree will, if let's say degree of SFD is 0, then for BMD the degree will be 1. That means if the SFD is a horizontal line, then BMD will be an inclined line. So just remember these points. Now I will take example directly to demonstrate you these things. It is very yes. We have a load W acting on this cantilever beam. The case is cantilever beam with point load, cantilever beam with point load, and this is length L. Okay. Now, how the diagram will become? As I told you. So here it's just a point load. There is no load diagram. Now I have to draw a shear force diagram. So first of all, I will draw the FBD, free body diagram. W. So there is one reaction in y direction, which is equal to if we do summation Fy equals to 0, then Ry reaction in y direction minus it is acting in the downward direction minus W equals to 0. So reaction in y direction has a magnitude W. If you do summation of moment about z axis equals to 0, then there is just one this reaction mz. It is anti-clockwise, and this it will cause a clockwise movement plus W into L equals to 0. So mz equals to W into L. So this is W into L in the anti-clockwise direction. So now let us first draw the SFD. Do you see any diagram here? Any rectangle, triangle, nothing. So now we will draw the shear force diagram. For that, I told you what is our first diagram with 0 degree. It is a horizontal line. That means let us see how it works. So now this load will go upward. It will go straight till the end. Now this is positive W, this is negative W, and it will come down. So this was above x-axis, so this was positive. Fine. So this is our SFD. Now SFD is a horizontal line, you can see, with degree equal to 0. Now BMD will have a degree plus greater than 1. So the degree will be 1. I also told you if the beam is sagging, then positive, and if the beam is hogging, then it is negative. So now if you see, if you imagine this beam and I am applying this load, so it is sagging or hogging? Tell me just here. I will just go back. So this is sagging and this is hogging. So this is what is now, what it is happening to the beam. So it is bending downward, that is hogging, and it is negative in nature. So our bending moment diagram will go below this line. It will go below the, it will go in the negative quadrant. So here we are. At the free end, it is 0, always 0. For cantilever beam, at free end, the moment is 0, and it will be an inclined line like this. So now what are the magnitude? It was here W and here it is L. So the magnitude of BMD is equal to area of SFD. So what is the area of SFD? W into L. That is what is your uh, magnitude of the bending moment. So this was one case. Now let us go through another case. Cantilever beam with uniformly distributed load. So this is a cantilever beam subjected to uniformly distributed load over its length L. Fine. Now we have to find it SFD, make its SFD and BMD. So first we have to find the reactions. As I told you, go for the hill, that is your FBD. So what will be its equivalent point load? Its equivalent point load will be area of this diagram W into L. It will act at the center. So this is L by 2. So this is your Ry, and we are not going to be bothered about the horizontal reaction because only the loads which are perpendicular to this beam are going to hurt us. The axial loads are not going to bother us. So, and the other thing is mz. So this is mz. So we will do summation fy equals to 0. It will come ry equals to wl. Summation of moment equals to 0. Mz is in negative direction. Mz equals to wl into L by 2 will be wl square by 2. Load into perpendicular distance. So now we have this with us. We have the bending moment as well as we have reaction. Now let us draw our shear force diagram. Now here the degree is equals to 0. So what will be the degree of now shear force diagram? It will increase by 1. So it will increase by 1. So yes. Now at the center we have W into L. Uh, at the reaction we have W into L. So it will go up by a distance W into L because that is the reaction nature of reaction. And now what will happen? The shear force, it is a rectangle. No, it is a rectangle. So it has to become a triangle now because after the degree will increase by 1 and will be equal to 1. So now it will go on decreasing. So this is how shear force diagram looks like. SFD. Yes, it is in positive contour. Now coming to the bending moment diagram once again. Now what will happen to your bending moment diagram? The beam, if you sit on this on a beam, that will be a uniformly distributed load, and it will go downward. It will sag. Oh, sorry, it will hog. There will be hogging, and hogging cause the BMD to be negative. So here we have this once again. At the free end, the bending moment will be 0, and at this end, it will have the maximum value. At this end, it will have maximum value. So now this is degree equals to 1. So for BMD, degree will now increase. Now the degree will increase by 1. So it in for SFD it was 1. So for BMD it will be 2. So what will we see? We will see a parabola. So we will join these 2 points with the help of a parabola. Sorry, the curve is not coming properly. Yes, bingo. Now what is the magnitude of this bending moment? It is important. The magnitude of this bending moment is equals to the area. So BMD is equals to area of shear force diagram. So the not BMD, it is just bending moment. Magnitude of bending moment is equals to area of shear force diagram. Now what is its area? Its area is half into base into height. So area will be half into WL into L, it will be WL square by 2, which is equal to our reaction. So the diagram is correct. This is now we have sorry third condition in which we have cantilever beam subjected to both point load as well as uniformly distributed load. So this is a bit complex position that we are dealing now. Here we have a UDL small w and a point load capital W and the length is L. Okay. So go for the kill. What is the kill? FBD is the kill. So there should be a reaction in y direction and there should be a moment of z axis. One load is at this end, the other load will be acting at the center with magnitude W into L. Now do summation Fy equals to 0. If you do this, your reaction in y direction will come out to be W plus W into L. If you do summation of moment about z axis equals to 0, your moment will come out to be mz equals to W into L plus W L square by 2. So this is your moment. Now how we will be making its SFD? A tricky question now. It has two diagrams. There is point load for which we have a simple rectangle. So we will go up by the amount of point load, that is W, and at this end we have just point load W. For point load, let me draw the diagram first. So this is the diagram for point load, nothing but a simple rectangle. What is the magnitude here? The magnitude is W, plus there is this additional uniformly distributed load. What is its magnitude? Magnitude is W into L, and since it's a rectangle, now the degree will increase by 1, and this is how it will look. This is WL and this is W. So if you look closely, so reaction is at Y, Ry here. If you see it here, reaction at Y is W plus WL. So here is W and here it is W into L. And now we will draw the bending moment diagram. So the bending moment diagram, this is L. Once again, the beam will be bending downward, that is hogging. So the bending moment diagram will come in the negative quadrant. So let me draw quickly the bending moment diagram. Okay, it will go in the downward direction. So for this we have let me just check it. Yes. Now the if I make it clear, so this line does not appear. Let us just make it properly, so that you can draw the diagram and get the idea properly. Yes. So this is how it will look. Fine. Now, when we go for the BMD, we have to look at this diagram. So at the free end, the bending moment is zero. Here, the bending moment is zero. At this end, we have the magnitude of the bending moment is maximum. So what is its magnitude? The magnitude of the bending moment is equals to area of the SFD. What is its area? If you look closely, there are two diagrams. One is a rectangle and the other one is triangle. For rectangle, the area is W into L, width into height, or width into height. And for this triangle, we have the equation half into WL into L. So the equation becomes WL plus WL square by 2, which is similar to this value. So that means our diagram and our calculation are going to be correct. So this is how it looks now. The degree. So now the degree must be 2, right? So for degree 2, we will draw our. So this is how we solve these problems in GATE. We have to go by this moment. This method is called area moment method. This is very much used in deflection as well. So I will uh, encourage you to go for more such cases on simply supported beam. So that is up to you to do it and take this mantle forward for this chapter. Simply supported beam. Do for just only two cases, point load and UDL. That will be sufficient for your GATE exam, because the GATE examiner, the paper setters also know that it is not possible to draw entire SFD BMD and draw and do point to point calculations. What they are interested in is in concepts. So go for concepts, solve this by yourselves, and if there's any question, you can get in touch with me. You can ask for my contact information from your coordinators. So this is how we deal with SFD BMD for from the GATE point of view. Now let me uh, just summarize and reiterate what we studied in this session. The very first thing that we studied was what are the types of loads. Then we saw types of supports. Then we studied types of beams. Then we studied sign conventions, the hogging and sagging part. This is negative and this is positive. Then we studied, uh, then we took these cases on cantilever beam. What are the types of load? Point load, UDL. These two are important from exam point of view. What are the types of support? Hinged, roller, and fixed. There are two beams which are important from our exam point of view. One is cantilever beam, the other one is simply supported beam. Sign convention, I told you for sagging, it is positive. The bending moment diagram will go in the positive direction, and for hogging, it is negative. Cantilever beam, there were three cases: point load, UDL, UDL plus point load. So this is it for today's session. Thank you for being here, and we will end our today's session here. Thank you very much for listening. Have a good day ahead.